Earlier, when I discussed the history of concrete and cement, I mentioned to you that the early Romans used volcanic ash as a key ingredient in the making of their cement, and they called this ash pozzolana. Now, I'm not aware of many people using volcanic ash these days, but we do make extensive use of what we now call pozzolans. So there's a group called the American Concrete Institute. They've got a nice complicated definition based on the chemical properties of these pozzolanic materials and the way they react with the chemical elements in the cement. But we're going to make this a little easier to understand. And we're going to say that a pozzolan is a fine powder that acts like cement when it's used in a mix along with the cement. So this is sometimes also referred to then as a supplementary cementitious material. Now, I said I don't know of many people using volcanic ash these days, but we do use a material that's known as fly ash. Now, instead of ash that's left over from a volcanic eruption, this is ash that's left over in a power plant after it burns coal. It's what sits at the bottom of the furnace that would otherwise be a waste product. Now, instead, since it can have pozzolanic properties, we can use it to help make concrete. Now remember though, I said that by definition, this stuff only acts like cement when it's combined with the cement. So when I mix cement and water, it forms our paste. We talked about that earlier, and it's going to harden and bind all the aggregates together in the concrete. If I tried the same thing with just fly ash and water, I'd just get sludge. But if I use both the cement and the fly ash in the same mix, it undergoes a chemical process that replicates hydration, and we get hardened concrete. So the technical explanation for this is that when cement goes through the hydration process, it gives off what's called calcium hydroxide. The calcium hydroxide then reacts with the fly ash, and we form a brand new compound, and that compound acts like cement. So I can't replace all the cement with fly ash. I need both compounds to make this work, but I can replace some of the cement, which lets me use an industrial byproduct from a power plant that would otherwise be a waste product instead of manufacturing more cement. So it's a good thing. Now, not only that, but it also adds some really desirable properties to concrete. So in its plastic state, the tiny fly ash particles, they're almost spherical in nature, which makes them work like millions of ball bearings in the mix, and the mix becomes a little more workable. It makes it easier to use and place, and in some cases it might let me reduce some of the water content a little bit while still maintaining that workability. Now, the other thing that happens is as the hydration process starts, this process gives off heat. So in chemistry, hydration would be known as an exothermic reaction. Again, gives off heat. The pozzolanic reaction is a little different, and it gives off less heat. So the higher the fly ash content, the lower the heat it gives off. And sometimes this is really important in structures with a mass amount of concrete, like a dam, where too much of that heat can actually cause thermal cracking that we don't want. In the hardened concrete, the pozzolans are going to continue to react with all the freed up calcium hydroxide in the mix as long as it's continued to be given off. This generally means that concrete made with fly ash is going to continue to gain strength for a longer period of time, and the result is that after a few months, this fly ash concrete will be stronger than the same concrete made with cement only. And the other thing that happens is that when we use up that free calcium hydroxide in the pozzolanic reaction, we also get fewer what we call bleed channels in the hardened concrete, little microscopic voids. And this results in a more dense, less permeable concrete that's more durable over time. So what I want to make sure you understand here is that these things like fly ash, these pozzolans, they're not just a filler in concrete. They actually make it a better material. And I also want to make sure that you're following my description of the role these materials play in the chemical process of the hardening of the concrete. So this means that these materials have to meet certain requirements and have specific chemical properties. For instance, we can't use all types of fly ash. Coal in some geographic regions contains sulfur, and we don't want that in our concrete. Sometimes the ash particles are just too big, or they contain too much remaining carbon. These conditions would also prevent this type of ash from being used. So don't try to do this on your own. This really takes a trained and experienced concrete material technician to properly select and then proportion all of these materials when they're creating their mix designs. Another way to say this is not your father's concrete. We're absolutely leveraging our knowledge of chemistry these days to make better concrete. Now, used properly, these pozzolans, or supplementary cementitious materials, can really help us make better concrete. Now, I've mostly talked about fly ash here because it's the most widely used pozzolan, especially when we consider the volume of it. But there are other pozzolans out there like ground granulated blast furnace slag, silica fume, and even rice hull ash. And these are all industrial byproducts that can be repurposed to make better concrete. So all of these products are also sometimes put in a category that we're going to call mineral admixtures. And now that we have a basic understanding of what these mineral admixtures do, let's go on to our next topic, and we're going to take a look at chemical admixtures.